Okay, we'll go ahead and get started. Can everyone see the slide and hear me okay?
Yes.
Thank you. So what we'll do today is, for about the first 20 minutes or so, we'll start on chapter 14, which is kinetics. And then after that, I'll stop and you can take the quiz number 2. The other thing I wanted to mention is obviously we've had some snow and ice this week. They're predicting that again for next week. So one nice thing about having the Zoom set up is we'll have class next week, whether the campus is open or not, since people can Zoom in and see the class that way. So, all right. So chemical kinetics. What are we talking about when we talk about kinetics? Chemical kinetics centers around looking at the speed of a reaction. So the speed at which the reaction takes place, we refer to that as the reaction rate. And chemical kinetics is just studying how fast reactions go, and then beyond that, what can you do to speed up reaction rates or slow them down or things like that. One of the things that comes out of chemical kinetics is what you call reaction mechanisms. And the mechanism is, so when we write out our chemical equation so far, we've been writing it with reactants on the left, products on the right, and it looks like it's a pretty just one-step simple process from going from the reactants to the products. In reality, it usually isn't that way. Usually there's multiple intermediate steps in there. And so in the reaction mechanism, you're looking at each of those steps, even if they don't show up in the final product, reactant product equation. And you study those changes that occur, and once again, maybe you try and do things to speed up or slow down one of those steps. So there's 4 areas that we're going to talk about that affect reaction rates. The first is physical state of the reactants. The second is reactant concentrations. Third is reaction temperature. And fourth is the presence of a catalyst. So each of these factors influence the reaction rate. So we'll go into that a little bit more detail. So if we look at the physical states of reactants, what we need is we need for the reactants to collide, to actually run into each other, to have a reaction occur. And the more they collide, the more rapidly they react. So when we think about physical states, we usually think in terms of homogeneous reactions or heterogeneous reactions. And homogeneous reactions mean that all the reactants are in the same phase. And by that, we mean they're either all gases or all liquids. So in other words, they mix real well, and so you get more of those collisions that you're looking for. And a lot of times homogeneous reactions are faster than heterogeneous reactions because they're in that same phase. Conversely, the heterogeneous reactions, the reactants are not in the same phase. And what that usually means you have some solids present. And because of this, they're slower. One thing that can be done to kind of speed up heterogeneous reactions is to have the solid be a fine powder rather than just a chunk of solid sitting there. And the reason for that is it gives you more surface area, and more surface area then increases that likelihood of having the collisions. So in general, homogeneous reactions where all the reactants are either liquids or all the reactants are gases, those tend to go a little bit faster than the heterogeneous reactions. And the heterogeneous reactions, usually what you're talking about is some solid with a lot of times a liquid. And that'll be a little bit slower. The next part is reactant concentrations. So the more concentrated it is, that usually means it's a faster reaction. So if you have a reaction and you want to increase that rate by increasing the concentration of the reactants, that usually increases the reaction rate. Once again, as we said before, we're looking for these collisions to occur. And so if we have more molecules, we have more stuff there, it just increases the likelihood of the collision occurring. So that's why the concentration results in a faster reaction. The third thing, temperature. In general, increasing the temperature increases the reaction rate. And that's because kinetic energy of the molecules is related to temperature. So as that kinetic energy increases, the temperature increases. And the way to think of that is you increase the temperature, the molecules start moving around faster, and also they have more energy because you're adding energy into the system with that increase in temperature. If you increase the number of collisions and you increase the energy that the molecules have, well, both of those are going to increase the likelihood that the reaction occurs. So in general, once again, if you want to increase your reaction rate, you increase your temperature. And then the fourth thing is the presence of a catalyst. So a catalyst is something that you put into the reaction to increase the reaction rate, but the catalyst doesn't participate in the reaction in terms of forming a product. And catalysts usually aren't used up. They can be something called poisoned, and that's where they start to lose some of their activity, but that's not really a reaction in the sense of you take A, B, and C and form something new. So the catalyst won't show up in that balanced equation that you would write. So in other words, when you'd write reactants on the left and then what they form, the products on the right, catalyst wouldn't be part of that, whereas the reactants and products would be directly related. The way catalysts typically work is they change some of those intermediate steps in the reaction mechanism in a way so that the reaction goes faster. And it's usually related to lowering energy levels and things like that. And we'll talk about something called activation energy a little bit later in the chapter, which is really what catalysts are doing. Now, catalysts can be heterogeneous or homogeneous, either one. The heterogeneous catalysts a lot of times are metals or metal-like, and it's literally pieces of metal in that reaction. And if you think about it, metals like to donate electrons, so that helps in a lot of reactions, having that extra thing that'll donate some electrons. A lot of times catalysts also are homogeneous. In other words, they'd be the same phase. If it's a solution type reaction, then it would be a homogeneous catalyst in the solution. And like I said, we'll talk a little bit more detail about catalysts a little bit later in the chapter. So when we talk about reaction rate, what we're really talking about is how often do the molecules collide? Because if they don't collide, we can't have a reaction. And then they also need to have the right orientation. So just because they collide doesn't mean you get the reaction you want. You have to have the correct orientation of the molecules when they collide. And then you need to have the appropriate amount of energy, because usually in a reaction, what you're talking about is you're talking about breaking some bonds. And if we remember from before, we said if you're breaking a bond, you got to put energy into the molecule to break that bond. So you have to have a collision first of all. The collision has to be oriented the right way. So in other words, the right parts of the two molecules have to be running into each other. And then that collision has to have enough energy so that you break the bond that you're trying to break before you form the new one. So all three of these things must occur in order for a reaction to take place. And that's one of the reasons why when you talk about reactions, you'll always hear people talk about side reactions. And so you're trying to combine A and B to form C. Well, sometimes you react A and B and you form something other than what your target is. And that's because one of these things that you wanted, either the orientation or the energy or something like that, wasn't exactly right. And you wind up reacting and forming something else. And that's where the notion of impurities in reactions and things like that come into play. Well, when we talk about reaction rate, what we're really talking about is the change in concentration. And that can be a change in the reactants or a change in the products over a certain time period. And the way we designate that is with this triangle, then the brackets divided by triangle and T. The triangle stands for delta, and delta means a change. And then those brackets, that's what we have for molar concentration. So molarity is how we express this stuff, moles per liter. And then the T is time. So that delta concentration divided by delta time is our change in concentration over whatever time period we're studying. So when we talk about this, there's three different types of rates that people will talk about. One is the average rate of the reaction. The second is the instantaneous rate of the reaction. And then the third is the initial rate of the reaction. So that average rate of the reaction would be if you calculated what the reaction rate was at different time points over the course of the reaction. Say the reaction took an hour and you collected samples every 10 minutes and determined the reaction rate at each of those. Each of those rates that you determine would be an instantaneous rate at each of those 10-minute intervals. But then but the number isn't the same over the course of the reaction. Reaction rates change with time. And so you could take all of those individual ones and average them out, and that would give you that average reaction rate, where each individual point's the instantaneous. The initial rate, that's the rate at time zero when you start. And the initial rate is usually the one that people are a little more interested in, just because that's usually the fastest rate of the reaction. It just gets slower from there. So let's take a look at an example here. So in this example, we have butyl chloride, C4H9Cl, reacting with water to form butanol and hydrochloric acid. So what we would be, our rate expression down at the bottom, we see a negative delta, then the concentration of that butyl chloride divided by delta T. It has a negative sign with it. That signifies that we're using up the butyl chloride. So in other words, any reaction rate that's expressed for one of the reactants will have a negative in front of that delta. That tells us that that's being used up, that's being reacted. The two things on the right, the butanol, the C4, H9OH, and the HCl, if we wrote reaction rates for those, it would be plus delta because that's being formed in the reaction. So once again, as we said before, the concentration of the butyl chloride is molarity, moles per liter. And then the time, that can be in seconds, minutes, hours, whatever. That kind of just depends on how fast the reaction is, what time, excuse me, what time units are used. So if you were to look at this, this is the kind of data table you would have, where if you wanted to calculate reaction rates for the butyl chloride reacting with water, you'd have something like this table. On the left-hand side, you have time values. In this case, time is expressed in seconds, so 0, 50, 100, 150, on down the line. And then you have the concentration of the butyl chloride at those times. And then what you would do is you would use that information and then calculate average rates. And I'll show you in a moment how that's done. But what I want to point out here is we see that initially the rate is 1.9 times 10 to the minus 4 molar per second. And we see it going down as we go over the course of the reaction. And that's pretty common. Usually as reactions progress, the rate decreases. And that's why I was saying you could go ahead and average out all these numbers to get an average reaction rate, but really the highest rate you're going to have is this initial one. And so that's the one that people kind of look at. The other thing about this is if we think about, well, why does that reaction slow down with time? Well, it's not so much that it slows down with time, it's that it slows down as our reactant concentration gets less. So we see the butyl chloride started out at 0.1 molar, and before it got to 0, it's down to 0.02 molar. And so remember, we said that one of the things that we need for the reaction to occur is we need the collisions to occur. And if it's more concentrated, then it's just, think of it as a little more crowded, and then you're going to have a greater likelihood of that collision to happen. So this just kind of reinforces what we said before, that reaction rate is dependent on concentration. And with time, we see that reaction rate typically going down. And that's usually because of the concentration decreasing, fewer collisions, things like that. So one of the things that you typically do with that data that we just saw is you plot it. And this plot we have on the right-hand side here shows the time on the x-axis, concentration of the butyl chloride and molarity on the y-axis, and then those different data points that we have. So those butyl chloride data points, someone would have pulled samples from the reactor and analyzed it to see how much butyl chloride was left in the vessel at each of these time points. And so that's how you would generate the points on this curve. We see a couple things. We see that it's not linear, okay? But what we can do is we can draw tangents to the curve and then calculate the slope of that tangent. And that's how, for instance, you get the instantaneous rate, and you can get other instantaneous at time 0, and you can get other instantaneous rates at any of these time points. So in general, people will plot this, then draw the tangents, and that's how you get your reaction rates. So any questions about what we've talked about so far? Okay, so I'm going to stop here. I just wanted to kind of get started on this a little bit because it's kind of a long chapter. I'm going to stop now, and please go ahead and log on to Canvas and take the quiz. It's quiz 2. Thank you.